All right, everyone. Welcome to EE 2950 SI session number 4. We're going to look at a few different analysis techniques that's going to build upon our previous knowledge. All right, so our first one we're going to look at is called the node voltage analysis or nodal analysis. And as the name implies, you're going to need a node for this. And what we're going to do is we're going to take the currents and we're going to pick a point where they meet, and we're going to sum our values up. Okay, so let's see what that looks like. So if we were to draw our circuit out, plus minus, this will be point VA, this will be point VB, and this will be point V of C. We'll have resistor 1, resistor 2, and then R3. And then down here, we'll call this point V of D. Okay. So to do nodal analysis, what we're going to do is we're going to combine some previous knowledge that we had. So we're going to use the first part of this is going to be the KCL. Okay. So what we're going to assume is that we have our currents, entering and leaving like such. And what we'll do is we'll say, okay, this will be I1, this will be I2, and this will be I3. All right. And we'll go and write our KCL out such that negative I1, negative I2, and then plus I3 is equal to 0. Okay. And you're more than welcome to do it the other way as well. So you can do plus I1 plus I2 minus I3 is equal to 0. I'm going to be using this version just because that's what your textbook uses. Okay, and what we're going to do is we're going to employ V is equal to IR into this equation. Okay, and we're going to use the concepts of voltages at a point. So what does that mean? So notice how we put VC, that is much too big. How we put VC, VB, VA, and then VD. What we'll do is we'll say, okay, I'm going to start at V of A, and I'm going to go to V of B. So I will write out, and real quick on the side here, so we'll just do I is equal to V over R. So that's the translation here. Okay, so what we'll do is we have negative I1 is going to be V of A minus V of B over, and we're crossing R1, okay, with that current. So that'll be R1. All right, we'll jump over to I2. I2 is going to be, we'll do negative V of C minus V of B over, we're crossing over R2 with current 2, so we'll do R2. And then we'll look at R3, or I3. So I3 is going to go from V of B all the way down here to V of D. So we will write plus V of B minus V of D over R of 3, because we're crossing through the R3. We're crossing through that R3 right there. Okay, so Something that we need to know to do a nodal analysis, though, is we need something called a reference point, and this comes in the form of a ground, okay? And we call that V of G, or V of capital G. And what that means for us is that there are 0 volts there. So ground means that there's 0 volts. And we'll notice that our point V of D is the same point as V of G. So here, V of D is equal to V of ground, which is 0 volts. Okay? And all we have to do is we're going to plug in known values into our equation. So we'll plug in knowns, and we're going to solve for our unknowns. Okay, and we're going to see what an example of this problem looks like in just a bit. Okay. Mesh loop analysis. So what is mesh loop? So once again, as the name implies, we need loops. So if I go and draw circuit out for us, and we're going to actually draw the same circuit as before. R1, R2, R3, and that looks like all we need. Okay, and what we're going to do is we're going to say that we can identify there's 2 loops here. So we can do loop 1, and then we can also do loop 2. All right, and what we're going to say is with these loops is that we're going to follow our current I1 on the left loop, and we'll follow our current I2 on the right loop. And we're going to have a point here where those 2 currents are going to meet, and they're going to form this thing called I3. So what we'll do is we'll come to the side here, and we'll just write this out first. So if I1 comes in, I2 comes in, they form I3. So I3 is going to be equal to I1 plus I2. All right. So when we write that out, what do our loop equations look like? So for our first loop equation, put loop number 1 here. We're going to do a KVL on it. Okay, so we're going to sum the voltage to 0. So like before with our KVLs, we'll just pick a point and we're going to walk around the circuit. And here I'll call this one V of A. Why not? And I'll call this one V of B. Sure. Okay, so let's walk around here. We'll hit negative V of A, loop 1, V of 1 right here, positive, negative, positive, negative. Right. So we'll come in, we'll hit the positive terminal of V of 1, and then we'll come down the middle branch and we'll hit the positive terminal of R3. So that'll be positive V of 3, and that'll be equal to 0. All right. And what we're going to do now is we're going to replace it with V is equal to IR, but these are going to be specific to each element. So we'll come in here and we'll write negative V of A. V1 is going to be equal to I1 times R1, because it's the R1 resistor with I1 running through it. And then we'll say for V of 3, I of 3 times R of 3. and that'll be equal to 0 because R3 has I3 running through it. Okay. Then what we can do is we can come now to number 2, loop number 2, and we'll do the same thing. So we'll hit the negative terminal of V of B, hit the positive terminal of V of 2, and then we'll hit the positive terminal of V of 3, and that'll be equal to 0. And then just as before, we'll replace the V's equal to IR, so negative VB plus I2 times R2 plus I3 times R3, and that'll be equal to 0. I2 and R2 is because the R2 resistor has I2 running through it, and then I3 for the R3 resistor is because we have I3 running through it. All right, and we'll notice here that we have I1, I2, and I3. Those are 3 different unknowns, and you'll know what V of A, the resistances are. You'll know what V of B is. You know what the resistances are. But now you'll have I1, I2, and I3, and that creates 3 unknowns with only 2 equations. Not good. But we actually have a third equation over here. So we can come in here, and everywhere we see I of 3, we can replace it with I1 plus I2. I1 plus I2. So now we only have 2 unknowns with 2 equations. And we can solve that, okay? So essentially all we're doing is setting up a system of equations. So set up a system of equations. Okay, and then you solve for your unknowns. Now, how do we solve for those unknowns? I'm glad you asked. Let's take a look. So we have everyone's favorite method, plug and chug. And we may or may not be familiar with a different method called Cramer's rule, which is a little bit more complicated, but very, very useful. Okay, so let's just set up a real simple system of equations. So if we do x plus 3y is equal to, say, -1, then 5 of x plus 4 of y is equal to, like, -7. Okay, so I think everyone's pretty familiar with the plug and chug method of, okay, we'll set y is equal to -7 minus 5x divided by 4. Then you'll come in here and you'll do x plus 3 times -7 minus 5x over 4 is equal to -1. Then you'll solve for x. And then you'll come back and you'll solve for y by plugging it back in. Okay, so that's, I mean, it's just very basic plug and chug. What I want to show you is Cramer's rule and what Cramer's rule looks like. So Cramer's rule involves using matrices, which I hope I spelled that right. Probably not. Okay. So what does that look like? So if we were to take the x's and the y's, and we took our constant values and we put them in matrices, we can actually go through and solve for the unknowns. So let's see what that looks like. So if I come in here and I will put x's here, y's here, and I'll come over to this equation and I'll look at coefficients on the x's, and it looks like on the first one I have 1x. On the second equation, it looks like I have a 5. Okay. Then if I come and look at the y's, it looks like on the first equation I have a 3, and the second equation I have a 4. Now, here, what we're going to do is we'll put our unknowns. So we'll put our x and then y. So these are our unknowns. Okay, so once we have that, then we can take this side over here and we'll call this our knowns. So our knowns are just going to be -1 and -7. We're just pulling from the right hand side. So knowns. Fine and dandy, what do we do with all this? Well, we can take a thing called a determinant. And what a determinant is, if we took A, B, C, and D, a 2 by 2, we can say A times D minus B times C. So AD minus BC. Now, what we'll do is, to solve for unknowns, we can say, all right, I want to find, say, the value of x. All right. What you'll do is you'll take the determinant of your coefficient matrix, which is this little bad boy here, coefficient. But what you're going to do is, in the column of the variable you're trying to find, so in this case x, you're going to replace it with your knowns column. And I'll make it real easy to see. So this will be -1, -7. And since we're not trying to find y, we'll just replace y, so 3 and 4. And down here in the denominator, we'll do a determinant of just the coefficient of matrix. So that'll be 1, 5, 3, and then 4. All right. And what we'll do is we'll just do a bunch of cross multiplications, kind of like we did before. And what we'll get here is, we'll get -1 times 4. This is AD minus 3 times -7. BC. We'll come down to the bottom and we'll do the same thing. So 1 times 4. So this is AD minus 3 times 5. BC. And this should give us, let's see, -4 minus 21, -21. This will give us 4 minus 15. So that'll give us 17 over negative 11 for a value of x. Okay. Now, if we want to find y, it's the same exact process. We'll just do y is equal to determinant of, now since we're finding y, we'll take that constant, the knowns, and we'll replace the y column. So minus 1, minus 7. We'll keep the x's, 1 over 5, over determinant, and it's going to stay the same in the bottom. So 1, 5, 3, and then 4. Okay, and so when we do this, we'll get 1 times negative 7 minus negative 1 times 5, A, D, B, C. And then we'll get 1, 4 minus 3 times 5, A, D, B, C. Okay, and it's just from that multiplication there. All right, and when we do this, let's see. Looks like that's negative 7 plus 5, which will give us 2. And then we already found the denominator value, which was negative 11, and that'll actually be negative 2. But negative 2 over negative 11, which is just equal to 2 over 11, which is our value for y. Okay, so this is just a different way of going about it. It's up to you really what method you use. However, in more complex situations, it might be better for you to use the Cramer's rule. All right, well, I will see you in the problem videos.